Imagine a highly skilled dancer performing a complex routine who suddenly finds themselves in a position where their arms simply cannot reach a critical point, no matter how hard they try. Or picture a powerful crane, loaded with cargo, getting stuck in an awkward stance, unable to complete its lift. This challenge of restricted movement is a fundamental concept in robotics. At Singularities, a robot manipulator experiences a critical reduction or a complete loss of its ability to move freely in all possible directions. In essence, the robot temporarily loses its dexterity and may become uncontrollable for specific tasks, which can be a significant operational hurdle. The core reason for this loss of manipulability lies in the mathematical relationship between the robot's joint velocities and its end effector's linear and angular velocities. This relationship is captured by something called the Jacobian matrix. At a singular configuration, this Jacobian matrix loses its full rank. When the Jacobian matrix loses rank, it means that certain directions of end effector motion become impossible to achieve, regardless of how the joints are moved. Furthermore, to try and achieve even tiny movements in these restricted directions, the robot's joints would theoretically requiring infinite velocities, which is physically impossible. This phenomenon is not a mechanical failure but a fundamental kinematic limitation of the robot's design. Understanding these points allows engineers and programmers to proactively manage robot behavior. Robot path planning algorithms are often designed to identify and circumvent singular configurations to maintain smooth and continuous motion. Additionally, designers consider a robot's kinematic structure carefully to ensure that critical singularities are outside the robot's typical operational workspace, or they might introduce redundancy into the manipulator to provide alternative joint configurations for reaching certain points. A useful concept for visualizing this limitation is the dexterity ellipsoid. This ellipsoid graphically represents the robot's manipulability in its operational space, indicating how easily the end effector can move in different directions. At a singularity, this ellipsoid dramatically shrinks or even collapses into a line or a point, visually confirming the loss of dexterity and the constrained motion. Recognizing these configurations is vital for robust robot control. Ultimately, understanding robot singularities is not just about identifying points of failure. It is about mastering the kinematic design and operational planning of robotic systems. By knowing why and where these limitations occur, we can engineer more reliable, efficient, and versatile robots that perform their tasks without unexpected stoppages or loss of control, ensuring smooth and predictable operation in diverse applications.
If you love robotics, like, subscribe, and keep building with us.